All right, this is 1-5, day 3. So we're going to look at keep looking at analyzing graphs of functions. We're going to start with a couple of review questions too in today's notes, just to hit over again average rate of change, and then talking about increasing, decreasing, and max and min. So we're going to kind of pull together our essential questions from day 2 first, and then we're going to move on to our last essential question of section 1-5, which is how can I identify even and odd functions. So hopefully by the end of today's lesson, you'll be able to determine what does it mean to be even and what does it mean to be odd for a function. All right, but let's talk about some of those review ones first. So here's what we're going to start with. We're going to do analyzing a graph of a function and talk about the open intervals. So again, open meaning they're using parentheses because when you're at the top or bottom, you're not actually increasing or decreasing anymore. So we're using parentheses on which the function is increasing, decreasing, or constant. And when they say open intervals, they're talking about intervals of the domain. So we're looking at the x values. And then we're also going to locate and classify maximum and minimums. Locate means, hey, what's the ordered pair? Like, where is it? So that's the where question. And then classify means the what. Like, what kind is it? Is it a max? Is it a min? Is it relative? Is it absolute? So it's kind of the where and the what. So we're going to do all that. So first of all, let's go ahead and get that graph. Now, we don't want to necessarily have to graph this like by plotting points. So let's go ahead and use our graphing calculator and type that in. All right, so I'm taking a look at my graph here. So I typed it into my y equals. Go ahead and graph the regular window, and we can see what's happening as this graph goes through. So I'm going to go ahead and take a picture of this so I can draw on it, and then we can talk about what's happening in each of these locations. All right, so let's take a look. I just wanted to have a picture so I can draw on this a little bit easier. Intervals where it's increasing, decreasing, or constant. So remember, we're reading our graph and we're always going left to right. So let's talk about what this graph does. So for the first part of the graph, it is increasing. And remember, there is an arrow here. So it's going to start from infinitely small here, but it's going to be increasing as we go left to right till we get to that location. So for this part of the domain until we get to here, the graph is going up. All right, then what happens? Well, then it's decreasing. So this part of the graph is decreasing. So this part of the domain, it's decreasing. And then once again, starting at 0, this graph increases again. So an x value of 0. So it's increasing again here, which means for this part of the domain, the graph is going up. So we had an increasing first, and then decreasing, and then increasing. So we're going to try to describe the intervals of the domain where that's happening. All right, so how would you describe this first part of the graph here, where it's increasing? Well, starting down at this end of the graph, that's negative infinity, it stops increasing, right there. And if you're looking at your graph, about what x value does that look like to you? Well, we can kind of guesstimate on the graph, can't we? So we could say, gosh, that looks like about negative, what, 2? It might be nice to know the location of this point before we start doing increasing and decreasing, right? To be able to actually say for sure what that looks like. And then the same thing for the next part, like, where is this point located? It would sure be nice to know that because that's where it changes direction from decreasing to increasing. So let's locate, that's the where, and classify those points first, and then we're going to be able to tell what's happening. So hopefully you remember how to do that on your graphing calculator. We can kind of, like I said, we can kind of make a guess, but it would sure be nice to know for sure. So we're going to go to second, calculate. Let's find that first point. What kind of point would you say this one is that's in quadrant 2? Well, it's going from increasing to decreasing at this location right here. So I would call that a relative. See if we can classify now. So a relative maximum, because it's going up and then down, so it's a max. Why is it relative and not absolute? Well, there's points higher in other locations. So remember, a relative, or the other word we used was local, so you could use that word as well. Relative to the points around it, it's a maximum. But there's other points on the graph that are definitely more than that one. So let's find that maximum. So we're going to use our graphing calculator here. We want number 4, which is a max. We're going to do our left bound, which is to the left of where that location is. We're going to do a right bound where the point is to the right of it. And then we're going to do our guess. And again, the guess is to help us figure out if there's more than one. Okay, so what do we do if we get this negative 1.999? Maybe you got negative 2.00000. That happens sometimes. Maybe you got an actual negative 2. If you see the 99999 or the 0.00001 or something, that's just the calculator saying, I'm not dealing with all the decimal places. It's the integer value. So this is at negative 2, 3. You can always plug it into your graphing calculator and look at the value of the function there to know that that's the biggest. But when you see all those 9s or all those zeros, go ahead and round to the nearest integer. So that's negative 2, 3 is that location. So this is at the relative maximum. So negative 2, 3 is the relative max. Go ahead and repeat that process in your calculator and get the relative min that we're looking at down here for this graph. So if you can calculate that relative minimum, then we're going to be able to, a little bit easier, be able to write what those intervals that are increasing and decreasing are. Okay, so I did my left bound, right bound, and then guess, and we get this. And I really wanted to talk about this because this happens a lot too. If you just looked at the graph, it sure looks like it's at 0, negative 1. And then we get this kooky like 9.0116 e negative 7. What does that mean? E is your graphing calculator's way of saying times 10 to the. It's your scientific notation. So basically this means 0.0000009 blah, 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 which is basically 0 if we're round to 0. So if you ever get something like that, and when you're trying to find a max and min, a 0, whatever, call it 0. So this point is 0, negative 1. So this location is a 0, negative 1. So we have a relative minimum or local minimum at 0, negative 1. Now I know it's relative because there are points on this graph that are smaller than negative 1, so it's not going to be an absolute. Okay, now we're going to be able to do our increasing and decreasing much easier because we know where these changing direction or points are. So we have our graph and we know what it's going to do. All right, so this graph is going to be increasing then, again I'll abbreviate, from negative infinity to where? Okay, so we were looking at this interval of the domain. It's changing direction right here at this location, at this point on negative 2, 3. What part of that point do we need? Well, we need the x value, right? Because we're looking at intervals of the domain. So from negative infinity to negative 2, this graph increases. All right, so then after that it decreases. So this part of the domain right here, so starting at negative 2 and ending at this location. Well, again, we need the x value, always the x value. So this graph is decreasing from negative 2 to 0, open intervals. So that's what these parentheses mean, open intervals. So they're not including the tops and the bottoms. And then what does the graph do? Well, starting at 0, it's going to be increasing. So this graph increases from 0 to infinity. Some people like to list it like I did, like in order of what happened. Some people put both of the increasings together and then the decreasing. Doesn't matter as long as you have them all listed. So that's really a big part of what we did in day 2. Being able to classify and locate maximums and minimums. What type are they? Where are they? Using your graphing calculator or just looking at a graph, and then being able to describe the increasing and decreasing. This graph had no places where it was constant. That would be where it doesn't change direction at all. All right, one of the other big things, or the other big thing we did in day 2 was talking about average rate of change. And one of the things that we do in this is talking about average rate of speed. Think about if you're at a stop sign and then you press on the accelerator and you start speeding up. When you look at the average rate of speed, the more you press the accelerator, what's going to be happening? Well, you start off kind of slow and then you get faster and faster and faster as you accelerate. So looking at that change in your average speed is a really good way to describe your motion. So average rate of speed is a great example of using an average rate of change because that's what you're looking for. So here's a great and really cool formula that's talking about the distance you travel in a moving car from stop and then when you start accelerating is given by this formula. So S of t. So S is distance and then the t is time in seconds, because we're accelerating pretty quickly. So when you press on the accelerator, what's going to happen? So how far you've traveled is given by that equation. Notice that the t is raised to a fractional power. That's okay. We can deal with that. So we want to find the average rate of speed of the car. Let's take a look at this first scenario. From time equals 0 to time equals 4 seconds. All right, so at time equals 0, that means you haven't started moving yet. So like you're just sitting at the stoplight or the stop sign. And then after 4 seconds, so what's going to be happening? So we're going to look from time 1, which is 0 seconds, up to time of 4 seconds, time 2. All right, so what's going to happen to our average rate of speed between those two locations? So we're going to find that slope of the secant line. Remember how we talked about the steepness and direction of that? Think about it. If you're speeding up, do you think that's going to have a positive slope or a negative slope? Well, you're increasing, right? So that should be, your second value should be more than your first value. So we should probably be having a positive slope here. So let's see if we can calculate that average rate of speed. So I'd be taking the speed of the second time minus the speed of the first time over T2 minus T1. So check and think about, well, how that fits into the average rate of speed we talked, or the average rate of change we talked about yesterday. That slope of the secant line, rise over run, the y values over the x values. Well, we're not using y and x now, but the y is your s of t and your x is like your t. So it's the same format. So we're going to calculate the value of the function at each of those numbers and then see what that slope is. So let's go ahead and calculate that slope. So this is the average speed equals. All right, so let's go ahead and calculate each of these. So s of time 2, so s of 4 seconds minus s of 0 over 4 minus 0. Let's see what we come up with. So if we plug 4 in here, so let's go ahead and do this calculation. That would be 20 times 4 to the 3/2 power. Now I'm going to talk about it, but you can type it into your calculator, but let's see if we remember what 3/2 power means. Remember, the bottom is the root, and then the top is the power that you raise it to. So square root of 4 would be 2, and then 2 cubed would be 8. So this would be the same as 20 times 8, which is going to give me a grand total of 160. Now, if you're not a believer in that, or that it's kind of hard for you to follow, go ahead and type it into your calculator and see what you get. So you can see by typing it in, we can do that calculation as well, and we can see what's happening on that. So it looks like that would be 160. So we have our average speed is equal to, oops, 160 minus, okay, s of 0. If you plug 0 in for t, 20 times 0 to any power, well, 0 to any power is just going to be 0. 0 times 20, still 0. So that's going to be 0 over 4 minus 0, which would be 160 over 4, which is going to be 40. And let's think about what units would be. Distance is in feet, and time is in seconds. So my average speed would be 40 feet per second. Remember, it's a rate. Remember, rates are things that have different units. So feet per second, that would be my slope or my steepness. So increasing, going up. So let's think about this in another way. What if I graph that function? So I'm just using x for my graphing calculator. If I look at the graph, I can see that this graph is increasing very rapidly. It's going up at a pretty quick rate. What if I looked at the difference in those values? I could use my table. From time equals 0 up to time equals 4, I can see that 0 to 160. So if I average out that as a rate of change over those 4 seconds, it's going to be 40 feet per second. So if I've gone up to that 160 distance over 4, just think about what that means. It's increasing. Now watch what happens as it goes on from there, though. It continues to increase. Would that rate of change if I look at a different time increment? So if I'm not looking from 0 to 4 seconds, how does that differ as I continue on? Would the rate of change be different? So let's take a look at from 4 to 9 seconds. So I'm going to go ahead and change my scenario here. I'm going to get rid of this so I can keep the same information up here. All right. So if I start with my time 1 as being 4 seconds, where I just was, and then to 9 seconds, I'm going to do that same calculation. So I'm going to take the distance it's traveled at the second time minus the distance it traveled at the first time over time 2 minus time 1. See if this is different. Is it still going to be 40 feet per second, or is that going to be something different? So we need to calculate s of 9, so after 9 seconds. So I'm going to use my graphing calculator as a little help here because I have it typed in there. At 9 seconds, it looks like it's 540 feet. So that's doing 20 times 9 to the 3/2 would be 540. Okay, where does that come from? Well, 9 square root, remember the root's on the bottom, so the square root of 9 is 3. 3 cubed is 27, so this is 27 times that 20, so 540. So we've got 540 minus the, should probably say this, s of 9 minus s of 4. So my s of 4 was 160, I believe, over my 9 minus 4 seconds. So let's go ahead and do that calculation. So 540 minus 160 would be, all right, gives me 380 divided by 5. So my average speed, so we're looking from 4 seconds up to 9 seconds. So that would be 380 feet over 5 seconds of time, which when you divide out, I believe that's 76 feet per second. So when we go from 4 seconds to 9 seconds, my average rate of speed actually increases. It's going 76 feet per second now. And think about it, as you accelerate, you keep going faster and faster and faster, right? So it starts off as a slower rate, and then it gets a little bit faster. So average rate of speed can be different depending on what part of the domain you're looking at. So what happens here? So it's a really cool example of an average rate of change. That's all that is. It's rise over run on the value of the functions over the value of the time or the x that you're looking at. So a really great example of what we talked about yesterday for average rate of speed. Let's get into what we're going to talk about for today, kind of the new piece. I'm going to talk about even and odd as our last little chunk here. So those are some review questions. So what does it mean for a function to be even, and what does it mean for it to be odd? And there's a really straightforward definition. It has to do with what symmetry a graph has. So think about what it means when you think of things that are symmetric. Things are the same on one side as they are on the other. We're going to talk about symmetry with respect to each of these. So a function is said to be even when it has symmetry with respect to the y-axis. So even functions have y-axis symmetry. Kind of a classic example of y-axis symmetry is a parabola, y equals x squared. When we think about a parabola, it's the same on one side of the y-axis as it is on the other. In other words, you can fold it over the y-axis, and it's going to be the same on one side as it is on the other. Odd functions are said to have, or they're said to be odd when they have symmetry with respect to the origin. So odd origin. I remember they both start with O. That's a great way to remember that. Odd symmetry means they're symmetric with respect to a point. And this is a little bit different kind of way to talk about something. But if you have origin symmetry, you're always going to have a point on the graph that's equal distant through the origin with a point on the other side. So let me give you a great example of that. An odd function is something like y equals x cubed. We have the point 0, 0, 1, 1, 2, 8. But then we'd have -1, -1, -2, -8. Looks something like this. Origin symmetry means on your graph, you have points always that are equal distant on one side of the origin as the other, equal distance. So if I have a point 1, 1, I'm going to have a point at -1, -1. So they're equal distance from the origin on that line segment. So it's a way to be able to tell what kind of graphs are odd. They always are going to have what's called origin symmetry. So we have really great ways to be able to check for that, to check to see if something's odd or even. So let's see if we can write those out. Before we move on and do that though, do you think you can ever have symmetry with the x-axis to be a function? So can a function be symmetric with respect to the x-axis? If you're going to have x-axis symmetry, that means if you have something on one side of the x-axis, you'd have to have something exactly the same below it. In other words, you'd be folding over the x-axis. What do you think? So you have a point up here, you have a point equal distant down there. Would that be a function? Think about the vertical line test that we did, or the definition of a function. For every x, there's exactly one y. It's paired with exactly one output. Well, this graph would have a point above and below. So for this x value, there are two different outputs. So this is never going to happen. You're never going to have x-axis symmetry if it's symmetric, or if it's going to be a function. So it cannot be a function if it has x-axis symmetry because of the vertical line test. It would not be. You'd have two different values for y. So that's nothing that we'll ever have. All right, so let's talk about our test for symmetry then. How do you check to see? Because, I mean, I know we can look at the graphs, but sometimes the graphs are maybe kind of complicated, or we don't have the graph, we have an equation. Remember, we can have algebraic. What are the tests to check and see if something is either even or odd? So let's talk about how can we check from an equation to be able to tell. So let's talk about even first. If something is going to be symmetric with respect to the y-axis, that means if you have an ordered pair in your graph x, y, then you better also have the ordered pair opposite of x, y. In other words, think about your parabola. If I have the point -1, 1, then I better have the point 1, 1. So if the x changes sign, the y better be the same. They have to be at the same location. Another way of saying that is in function lingo, f of opposite of x, so like f of -1, has the same function value as f of x. They're the same thing. The outputs are the same. They were both 1. So to check to see if something's even, that's a really quick way to be able to do it from an equation. To check to see if something's odd, we do something very similar. If you have a point, an ordered pair on an odd function, then you have to have the opposite of both also on the graph. So remember this one, we had the point 1, 1. Well, then you'd also have to have -1, -1. Same distance from the origin, but on the other side. In other words, both the x and the y change sign. So in function lingo, that means f of opposite of x, like if I put in a negative for the x, it better be, we also better have then the opposite of f of x. So not only does the x change sign, so does the y. They both have to be opposite to have origin symmetry. So we can check from equations for even or odd by doing that check for those points. Are those points, are those ordered pairs actually on the graph? A lot of times people can tell from looking at the picture, but sometimes we do actually need to talk about what those were. Oh, and I could have put them right there because that's where they were. So hopefully you saw that the test for even and odd, they're right there for you, so you'd be able to tell. So let me go ahead and I'll write them on there again. So if something's going to be even, if you have the point x, y, then you should also have opposite of x, y, or in function lingo, f of opposite of x should be equal to f of x. So the value of the function should be the same. That's y-axis symmetry. For odd functions, if you have x, y, then you also need to have opposite of x and opposite of y. Or in function lingo, that means f of opposite of x better be the opposite of f of x as well. In other words, if the x changes sign, so does the y. They both change sign. All right, so we're going to try one. We're going to see if something is even, odd, or neither by looking at the equation. So we're going to practice one actually with an equation. So we're going to take this function. I want you to take a look at it. It's degree 2. So gut instinct, parabola. Think about what kind of symmetries parabolas have. They actually have something called a line of symmetry. My question is this the y-axis? Because if it's not, then it's not technically even. So in order to be even, your graph has to have y-axis symmetry. So if it's been shifted at all, it still might have a line of symmetry, just not the y-axis. And to be odd, remember that has to have origin symmetry. So we're going to do the checks. Not every graph is even or odd. Actually, lots of them have neither of those symmetries. Again, they may have other symmetries, but not those, so they don't have those special classifications. So let's check for even here first. So we're going to check for even, and then we're going to check for odd, and we're going to see what happens. So for even, the easiest way to do that, we can plug in and check to see if we get this scenario. So if we plug in a negative x in for x, do we get the same equation that we started with? In other words, is this sentence true? So let's go ahead and see if we can give that a whirl. So I'm going to do f of negative x, see what I get. So I'm going to replace every x with negative x and see if I get an equation that's equivalent to my original. All right, so let's see if that works. So if I take a negative x and square it, that would be positive, so that would be 4x squared. Minus minus would be a plus, so that would be plus 3x, and then plus 1. So that's what f of negative x is. Now I want you to take a look at that rule. Is that exactly the same as the original? Well, no, it's not. The sign here is different. So does this thing have y-axis symmetry? Sure doesn't, so that means it's not even. So those two expressions would have to be the same. We'd have to be able to fold and get that same answer. Let's check for odd. In order to be odd, we have to put in a negative x and a negative y. We've got to have negatives for both. If there's negatives for both, and then we get the same expression as we started with, then we know that we're going to have something that has odd symmetry. So the easiest way to do that, I like to think of this almost as a y. Sometimes that's easier for people. So I'm going to put in a negative for the y, and I'm going to put in a negative for the x. I'm going to put a negative in both spots. And see what happens. Now, if this is going to be odd, then what I need to do is I need to have, when I simplify this all out, I should get something that's exactly equivalent to the original. That if I put in negative x, it's also a negative y, and see if that's going to give me the same expression. All right, so let's go ahead and simplify over here. So this would be 4x squared plus 3x again plus 1, which would be looking pretty good. But if I'm going to go ahead and solve this for y, divide everything by -1, that's going to leave me with negative 4x squared minus 3x minus 1. Now, is this expression equivalent to the original? Well, no. So this isn't odd either. It doesn't have origin symmetry either. So this would definitely be categorized as a neither. We're going to take a look at the equation too when we graph it and see why that is. So to check to see, the easiest way to do this, to check to see for odd, we replace xy with opposite of x, opposite of y to see if that point is on there. That's what it means to be odd. For even, we replace the ordered pair with opposite of x, y. So in other words, just this y equals over here to see if we get that, that same as the original. If we don't, it doesn't have that symmetry either. Let's take a look at the graph. So if you take a peek at the graph, definitely doesn't have origin symmetry. There's no points on the other side of that x-axis. So if I take a look at this odd again, to be odd, you have to have origin symmetry. So here's the origin. If I take any point on this graph and go through the origin, I should have a point equal distance on the other side. Definitely don't have that. That's why this is a no. This equation was not equivalent to the original. It didn't contain those 2 points, so it can't have that symmetry. Now this definitely has line symmetry, or it's not line symmetry, a fold symmetry, but it's shifted over a little bit. It's not actually the y-axis. So an only way it can be even is to have y-axis symmetry. Well, it's not folding on the y-axis anymore, and this is why that equation didn't end up to be the same. We didn't have xy and then opposite of xy. That would be the y-axis symmetry. So yeah, it still had a line of symmetry, but it just wasn't the y-axis. So this one we categorize as neither one of them work. We need to practice this a bit more to be able to prove it. So we're going to try a few more. I'm going to show the arithmetic. Our categorization here is it even, or is it odd, or is it neither? So we're checking to see these 2 symmetries. So they're writing it in function language. So this is the function language. Sometimes to be a little bit easier, it's sometimes easier to say if I have the point xy, then I better have opposite of xy for even. It's the same thing. It's just sometimes easier for people to think about. And then if I have the point xy, which means like the original function, then I better also have opposite of x, opposite of y. In other words, put in opposites for both. Sometimes for people, that's an easier way to think about these. All right, so let's go ahead and see if this is true. So we're going to check for this first one. This is a linear equation, so f of x equals 5 minus 3x. Is it even, odd, or neither? Okay, so to check for even, we'll start with that. I'm going to think of this as y equals 5 minus 3x, and we're going to check and see if this is true. So I'm going to replace x with opposite of x, and y is just going to stay y because we're checking to see if it's even. So I'm going to check and see if I have both points on this graph. In other words, if I replace x with negative x, I should still get y as my output. Both of those ordered pairs should be on that graph. So minus a negative, that would be plus positive. So that would be y plus 3x. So my question is this expression exactly the same as the original? Are those equal? No, they're not. So if I plug in negative x, I did not get the same answer as the original f of x. So no, this is not going to be an even function. So that is not even. Let's try odd. We're going to do the same kind of idea. So we're going to replace y with opposite of y, and we're going to replace x also with opposite of x. And we're going to simplify. So over here we'd have 5 plus 3x equals negative y, but we're going to divide by negative 1. So we're going to get y equals negative 5 minus 3x. Now my question again is this expression equal to the original? Well, no, it's not. So that function is definitely not odd as well. Because remember, if I plug in a negative x, I should get the opposite for y as well. They should be equivalent, and they're not. I did not get the same expression. So this one is not odd, and it's not even. Those are not equal expressions. I didn't get the same thing. So this is not going to be an odd function either. So this one is going to be categorized as a neither. So for this first one, it wasn't odd or even, so it's a neither. And hopefully if you can take a look at the graph, we can see why. Definitely isn't symmetric with respect to the y-axis. And if we take any point on that graph and go through the origin, definitely not going to have a point on the other side. All right, let's go on to the next one and see if we can find even, odd, or neither. So we'll try letter B here. All right, remember to check for even. If we have the point xy, we better have the point opposite of xy, which means I need to replace x with negative x and see if I get the same output as I did for the original. So that's what even means. You have 1 point on one side of the y-axis, 1 point on the other. So let's go ahead and put negative x in everywhere you have an x and simplify. So that would be positive x to the fourth minus positive x to the second minus 1. Now my question is this y output exactly the same as the original? Yes. Okay, what that means is it is most definitely even. We're going to have that even symmetry. Just to double check, we need to check for odd as well. Usually if something's even, is it going to be odd as well? Maybe, but not always, and actually not most of the time, but it could be. Like think of a circle, something like that, not a function, but it would have some symmetries like that. So it wouldn't technically be considered one of those, but you might have a graph that makes you, I guess, wonder. So we should check just to be sure. Remember what odd means. If you have the point x, y, then you should also have opposite of x, opposite of y. So I should be able to get back to that. So that means we replace y with opposite of y, and we replace x with opposite of x, and see if we end up, oh, that wasn't a 4 out front, it was an exponent of 4, and see if we get the same expression as the original. So let's check and see if that is the case. Opposite of x squared minus 1. So here we know we get x to the fourth minus x to the second minus 1, but then when we divide by negative 1, those are not going to be the same as the original. So that's going to be an opposite x to the fourth, a plus x to the second, and a plus 1. This expression definitely not the same as the original. It doesn't contain those 2 points. So this one is no, it is not odd. It does not have origin symmetry. So when we think about this graph, it should actually only be folding over the y-axis, which is what even means. Even means y-axis symmetry. Let's check the graph. All right, so take a look at that graph, definitely folding over the y-axis, it's even. So a lot of people use the graph to help them kind of get their gut feel like, ooh, I think I know what this is. Certainly not odd, though, doesn't have origin symmetry, but definitely even. Okay, for the last one here, 2x cubed plus 3x, would this one be even? So let's take a peek and see what we think. So I'm going to check for even by putting in an opposite of x. Remember, think of this as y equals. Sometimes that's easier for people to deal with than having that function notation. So I'm going to replace the x with opposite of x and see if I get that same expression as I had for my original, because those 2 points for all values need to be on the graph. So let's go ahead and simplify that. A negative raised to an odd power would be negative, so negative 2x cubed, and then minus 3x. Okay, we'll take a look at that. Is that the same as the original? No, not at all. So that means this function is not even. The point opposite of xy wasn't on that graph. So we're checking in general. We're checking for all points at once by doing these ordered pairs, as opposed to just looking at specific examples. We're doing it for all of them. So xy, to be odd, would have to have opposite of x, opposite of y. In other words, replace the y with opposite of y. Replace the x with opposite of x, and we're going to see if we get the same expression back. Well, watch what happens for this one. I know that this would be negative 2x cubed and then minus 3x. We did that one. But watch what happens when you divide by the negative 1 now. We get back to 2x cubed plus 3x. Yay! Okay, that's exactly the same as the original. What does that mean? It means that this is an odd function. It has origin symmetry. Let's take a look at the graph. All right, so when you take a peek at the graph, notice you have points on one side of the origin that are equal distance from points on the other side. So it has that kind of that classic sort of like the x cubed cubic example that we used originally. So it's an odd function. So some functions can be just odd, some can be just even. Lots and lots of functions are the ones that are neither. They don't have either of those classifications. So kind of the big new picture for today, our essential question is the difference between even and odd. Even functions have y-axis symmetry, odd functions have origin symmetry, and we have this great way to be able to prove it by checking their ordered pairs. So we have that way to be able to tell.